Hello, today we're going to take a look at how to graph some trig functions. The first thing that we're going to look at is when we have some amplitude changes. So for sine and cosine, we want to start off with our basic function. I like doing this for our sine, cosine, secant, cosecant for all our basic functions of sine and cosine with this. So cosine has a maximum at theta equals 0, a 0 at theta equals pi over 2, minimum at pi, 0 at 3 pi over 2, maximum at 2 pi, and since it's an even function, it's going to continue this pattern as x approaches negative infinity. All right, so that's what our standard cosine function will look like. Anytime we have something that's multiplied by our trig function, we're going to have an amplitude change. So that is just going to cause our maximums to be multiplied and go, instead of being at 1, they'll be at 2, and that will happen with all our maximums. All our minimums, instead of being at -1, will be at -2. And then all our zeros will not change location, both x or y coordinates. So all this does is change the difference between our maximum and our 0 and our minimum and our 0. The same thing will happen for secant and cosecant because they're based off of sine and cosine. So cosecant of theta is 1 divided by the sine of theta. So what I want to do with this is let's graph 3 sine of theta first. Now our sine graph works in a way where we have our y-intercept as 0. Sine has a maximum at pi over 2, a minimum at negative pi over 2, 0 at pi, and so on. It's the same graph as cosine, just shifted pi over 2. All right. But what the 3 is going to do is cause all of the maximum points to go to 3 and all our minimums to go to -3. So let's erase all of our maximums and minimums. Our zeros stay the same. So maximum at 3, minimum at -3. So the x coordinates will stay the same, but our y coordinates just change to be 3 and -3. Now, I like graphing the sine or cosine first to graph the cosecant or secant, because wherever sine of theta is equal to 0, our cosecant is going to have an asymptote, because 1 divided by 0 is undefined. Here are all our asymptotes for cosecant of theta. So it's at all of our whole number values of pi. So 0 pi, 1 pi, 2 pi, negative pi, so on. Since it's the reciprocal, wherever sine has a maximum, cosecant is going to have a minimum. So it's going to be this parabola. Wherever sine has a minimum, cosecant has a maximum. And it's just going to alternate concave up and concave down parabolas over its entire domain. So the amplitude here deals with the distance between the maximum or minimum of the parabola and the axis. For tangent and cotangent, it deals with the slope between the 0 and the next point. It's going to be very similar to graphing one of our cubic functions. So here, let's look at this cotangent one. Cotangent of theta is cosine of theta divided by sine of theta, so it's going to have asymptotes wherever sine of theta is equal to 0, which is all of our whole number pi's. Tangent and cotangent all have zeros halfway between the asymptotes. No matter what the horizontal shift, vertical shift, period change, amplitude change, whatever, halfway between the asymptotes, it will be a 0. That might have to shift up or down with a vertical shift, but that's what it's going to be. 3 cotangent of theta, this 3 deals with this slope, except that cotangent decreases. So we're going to have this slope between the middle and the next point, so it's going to decrease like this. If you looked at a graph on a calculator or Desmos or something, you'd see that this is a little more smooth than I can draw, but you get the idea. Cotangent decreases over its entire domain. Now, when we look at tangent, let's change this one to tangent so that we get that experience. So tangent has our asymptotes at our odd pi over 2s because it's sine of theta divided by cosine of theta. Zeros halfway between the asymptotes. And then this 1/2 is the slope on either side, so it's going to be slightly wider towards the middle of the graph. And tangent is going to increase over its entire domain. So that's what our amplitude change is going to do to tangent and cotangent. Let's take a look at what changing b will do to the function. Now, our standard cosine graph is going to look like this. All right. But then cosine of 3 theta, for sine, cosine, secant, and cosecant, our period is 2 pi divided by b. So this function, b is 3, so our period is 2 pi over 3. So our y-intercept isn't going to change. So this point of 0, 1 is going to stay the same. Now the period is how much time it takes a function to complete a full cycle. So what we do is go out 2 pi over 3, which is not easy to do on this, this graph. 2 pi over 3 is somewhere in here, and we have another maximum. Halfway between our two maximums, we have a minimum. So that's going to be at 1 pi over 3. So that's going to be somewhere about here. And then halfway between each of those, we will have a 0. I promise on an assessment I'll give you a graph that is marked up the way that it will work out. You will have lines for all the appropriate values. And then it's just going to follow that same pattern with this. So it's going to be a lot more compressed if our b is greater than 1. So if we connected these, it's going to take a much shorter period to repeat values. And I did not do a great job with this original cosine. I apologize for that. Just doing some quick freehand of this. You get the picture. So when our b value is like this, where this is the same as secant of 1/2 theta, that's going to stretch out the function. It's going to have a much longer period because we do 2 pi divided by b, so 2 pi divided by 1/2. So our period is then 4 pi. So again, secant is a reciprocal of cosine, so let's graph our cosine function first. So cosine of theta divided by 2 keeps our y-intercept, and then it takes 4 pi, so it takes 4 pi, in either direction to repeat a full cycle with this. Then halfway between these two maximums, or two zeros, or two minimums, like we'll have the other type. So halfway between two maximums, we have a minimum. So we'll have a minimum at 2 pi, a minimum at negative 2 pi. Halfway between the 0 and the maximum, the minimum and the maximum, we will have a 0. So our cosine will look like this. So this is cosine of theta over 2. Then let's pick a different color for secant. So again, whenever cosine has a 0, secant has an asymptote. Cosine has a minimum, secant has a maximum. Cosine has a maximum, secant has a minimum, and it's going to follow this pattern over its entire domain. And then here are other ones that you can practice with. Let's take a look at what happens when we have a horizontal shift. So these are going to work, both our horizontal and vertical shifts, just like with our other functions. Like if we had square root of x plus 4, and that would shift it left 4. So this is going to shift this left pi over 4. So typically, tangent will have its asymptotes at our odd pi over 2s. So at pi over 2, 3 pi over 2, negative pi over 2, whatever. And all we're going to do is figure out where our asymptotes are going to be with the horizontal shift, and then we can get the rest of the graph easily from there. So all we do is take this asymptote at pi over 2, shift it left pi over 4, and we have our new asymptote. The one at 3 pi over 2, we shift it left pi over 4. This one left pi over 4. Then this one would be somewhere off graph. Halfway between our asymptotes, we have a 0. And it doesn't matter that we have the horizontal shift. It's just halfway between the asymptotes. Tangent's increasing over its entire domain. So our tangent graph looks like that. Our slope here, if you'd like more points, it's going to be 1 between the 0 and the asymptote, that first point. And even with points, I managed to make it look not super consistent, but it should look like this is our it's not that one, but it's one of our tangent graphs. Okay. And the same thing happens with any of our other ones. So let's say we have this sine graph where we've got the sine of theta plus 3 pi over 4. So all we're doing, this is shifting it left 3 pi over 4. So we can graph our standard sine function, and you don't even need to connect the dots unless you would like to. And all we're going to do with this is shift our points left 3 pi over 4. So each of these lines is a pi over 4. So we go 1, 2, 3. 1, 2, 3, 1, 2, 3, and then just do that for every single point. Or once you see the pattern, so every pi over 2, we have another, like we go from a minimum, pi over 2 has a 0, pi over 2, maximum. All right, and then it will look like that. All we've done is shift it left 3 pi over 4. So for tangents and cotangents, you want to just find your asymptotes, base everything off of that. For sine, cosine, secant, and cosecant, you can do a couple original points from your parent function and then just shift those. So let's take a look at some vertical shifts. And most of the vertical shifts are like our normal ones. If this instead had been like +2, all we would have done is gone 1, 2, up, and then, all right, there's our point. It's a little trickier, but still very doable when we have something like number 14, where we have 4 sine of theta minus 2. So our typical sine graph, let's go ahead and graph that. And sine is my favorite trig function graph, and I'd like to hear what all of yours are. It's a nice way to make some friends if you're in a new situation, like roommate in college or whatever. What's your favorite trig function? And, you know, find out things about one another. So typically our maximums are at 1, our minimums are at -1, and our zeros are at 0. The amplitude change of 4 is what we should do first. So instead, our maximums go to 4, our minimums go to -4. I like doing that one first because you can just multiply it. So then you can deal with the -2 of just bringing it down 2. So instead of our maximums being at 4, our maximums are at 2, and we can label like that. Instead of our minimums being at -4, they go down to -6, and then we don't need this anymore. And our zeros also go down too. So our zeros are at -2. So all of our x coordinates stay the same, but our maximums are now at 2, zeros are at -2, minimums are at -6. So at theta equals 0, we have 0, which is now -2. We have a maximum pi over 2, which is now at 2. A 0 here, a minimum here, a 0 here. So all we do is just readjust based on our new scale. And then we can connect those points and see what happens when we have an amplitude change and a vertical shift. If we had just a vertical shift, all you do is shift all the points down or up the appropriate amount. Now, if we have something that has a horizontal shift and a vertical shift, we will take a look at in the next video.